Hello everyone, my name is Younan. I'm a fourth-year PhD student from National University of Singapore. I'm very happy to share with you our work on GAN-based 3D carbonate digital rock reconstruction. We just got this work accepted by JGR. It will be published soon. This work falls in the field of digital rock physics. It has two stages. The first stage is to image the 3D structure of rock samples. Then, different types of rock properties can be obtained by numerically simulating different physical processes within the digital rock objects. X-ray micro-CT and SEM are commonly used to acquire digital rock images. Micro-CT scan is expensive and time-consuming due to the high expenses of imaging sensors and high sampling rate during imaging. SEM provides higher resolution and larger sample size than micro-CT. However, it only images the 2D surface structure. Therefore, micro-CT and SEM complement each other. It would greatly improve the quality of digital rock images if we could bridge them in 3D digital rock reconstruction. Following this idea, we propose a GAN-based method to reconstruct 3D digital rock images from sparsely spaced XY plane slices. This method would greatly save imaging time since the sampling rate along the axis is reduced. Moreover, it enables the utilization of SEM images in 3D reconstruction and thus significantly improves the quality of digital rock images. Before we get into the detailed workflow of our method, I'd like to introduce GAN first. Its full name is Generative Adversarial Network. It comprises two competing neural networks, namely a generator and a discriminator. The generator takes random latent vectors C as inputs and outputs various types of objects such as images, texts, and music. The discriminator takes the objects as inputs and predicts the probability of the inputs to be real objects. What is adversarial chaining? Let's take image data as an example. During chaining, the synthesized fake images and the real images are mixed and fed into the discriminator. The discriminator works on improving its ability to separate the real and fake images. At the same time, the generator works on improving its ability to synthesize realistic images to fool the discriminator. Under such adversarial chaining scheme, the generator will slowly learn to synthesize realistic images that can fool the discriminator and human eyes. Despite the popularity of GANs, their application is always limited by the low resolution of the generated images and mode collapse, as well as the unstable chaining process. Progressive growing GAN is thus proposed to conquer these problems. TGGAN achieves its best with three strategies. First, it adopts the proven optimal loss function for GANs, which is water-stand distance with gradient penalty, to stabilize the chaining process. Moreover, a mini-batch standard deviation layer is added towards the end of a discriminator, which increases the image variation. Last and most importantly, PGGAN employs a novel strategy to chain a neural network, which is a progressive growing chaining strategy. As denoted here, the structure of the generator and the discriminator will be shown on the top and lower half of the screen, respectively. The chaining process starts with low-resolution images of 4x4. Real images are downscaled to match the current resolution of 4x4 by average pooling. After the chaining loss stabilizes, convolutional layers operating on 8x8 spatial resolution are added to the generator and the discriminator simultaneously to increase the resolution. As chaining goes on, layers operating on increasingly larger spatial resolution are added to the discriminator and the generator synchronously, every time the chaining loss stabilizes. The resolution is progressively increased to 1024 by 1024 in this way. Such chaining strategy stabilizes and enables the generation of high-resolution images by breaking down the challenging end goal into simpler subtasks. It also speeds up the chaining significantly since most iterations are done at low resolutions. Since the inception of GANs, many researchers have been very interested in the low-dimensional latent space of GANs. Many studies demonstrated that the semantic concepts and pixel patterns are encoded linearly in the latent space. Thus, images could be edited from the latent space very efficiently, including image interpolation and manipulation. This is a very interesting example of latent space interpolation. In this project, a big GAN is trained to synthesize natural images of different species from latent vectors and class vectors. By interpolating between the class vectors, a tiger gradually transforms to a cat with its pose preserved in the picture. If both the class and the latent vectors are interpolated, a fox facing right will slowly transform to a dog facing left in the picture. Encouraged by such successful case of latent space interpolation, we propose our GAN-based method for 3D digital rock reconstruction. Here is the workflow of our 3D reconstruction method. First, a PG-GAN is trained to synthesize 2D micro-CT carbonate images. In our experiment, micro-CT images of an acid-dilate carbonate sample are used. Next, invert for the latent vectors corresponding to the scanned slices using gradient descent algorithm. The loss function is the pixel-wise L2 norm reconstruction error between the real and the synthesized images. Lastly, linearly interpolate between the inverted latent vectors, and then map them to the image domain using the generator of the PG-GAN, in which way the unknown slices sandwiched between the scanned slices are reconstructed. Note that the rock sample is divided into a chaining section and a test section. We use all slices from the chaining section and the assumed scanned slices from the test section to train the PG-GAN. If the test section slices excluded from the chaining data can be accurately reconstructed using our method, this means that the PG-GAN has satisfying generalizability because it is able to synthesize images outside the training data set. Based on the training data, we trained a PG-GAN to generate 1024 by 1024 grayscale carbonate images from 5 12-dimensional latent vectors. Here, 3 randomly synthesized images are shown in the first row. The zoom-in areas within the red rectangles are shown beneath them correspondingly. The synthesized images look very realistic. In the enlarged view, although the common checkable artifacts are observed, the face boundaries are sharp and clear. Here, 2 slices reconstructed from the interpolated latent vectors are compared with the ground truths. The top one is from the chaining section, and the bottom one is from the test section. The first to the third columns are interpolated slices, ground truths, and misfits, respectively. Both interpolated slices look realistic and visually indistinguishable from the ground truths. The misfits are nearly zero and randomly distributed within grains and pores, with only minor misfits at the pore-grain boundaries. Hence, we can conclude that reconstruction in XY plane is accurate enough. Moreover, the PG-GAN generalizes well to test data. The test section slice contains a bit higher misfits than the training section slice. This means that the reconstruction error can be further reduced with more training data. The axial structure is reconstructed by concatenating XY plane slices. This figure compares a real slice and the corresponding reconstructed slice in XZ plane. Firstly, the reconstructed slice presents continuous structure except for some mild linear artifacts caused by latent space interpolation. As pointed out in the figure, the grains, pores, and even thin cracks are well restored. There's nearly no difference in the reconstruction performance between the training and test sections, despite some stepped grain-pore boundaries in the test section. Again, it demonstrates that our method has satisfying generalizability. pole networks extracted from the real and reconstructed digital rock images are compared as well. The connected poles are plotted as tubes, scaled and colored with respect to the pole radius. As shown in this video, the real and reconstructed pole networks resemble each other, especially for large poles in red. Their porosities are very close, with only 0.1% difference. Therefore, our method accurately recovers the connected pole network, making it more probable to estimate fluid transport properties accurately. Here comes the summary. Taking advantage of the linearity of the latent space learned by PG-GAN, we propose a novel method to reconstruct 3D digital rock images from sparsely spaced 2D cross-section images. To be more specific, after a PG-GAN is chained, the reconstruction process has 3 steps. There are GAN inversion, linear interpolation between the inverted latent vectors, and the concatenation of the 2D synthetic slices from the interpolated latent vectors. In our experiment, the optimal scan interval is 9, hence we achieved 9 times speed up of the imaging process compared to full 3D micro-CT scan. Apart from that, the 3D digital rock can be restored from only the inverted latent vectors of the sparsely spaced slices. It leads to significant compression of the image data. In our experiment, the 1720 megabytes image data are compressed to only 0.375 megabytes latent vectors. What is more, the cross-section images could be either SEM or micro-CT images. Therefore, our method enables the integration of SEM and micro-CT images in 3D reconstruction and thus helps improve the quality of digital rock images. Last but not least, the PG-GAN is proven to be able to synthesize high-quality digital rock images with negligible computational cost. Hence, we can create a repository of PG-GANs trained on different types of rock images to enlarge the digital rock repository for future machine learning studies. I would like to end my video with an animation of synthetic XY plane slices. They are generated from linearly interpolated vectors between 2 random latent vectors using PG-GAN. It is very interesting to observe the smooth and continuous transformation of the rock structure. This shows the great potential of GANs in image editing. If you have any questions and comments, please feel free to contact us by email. Thanks for your time. Bye.